For our final speaker, before we go into our lightning talks, I want to invite Jacob Washburn up to introduce them.
All right. Okay, thank you. So it's my pleasure to very briefly tell you about the Genomes-To-Fields prediction competition that we carried out this past year and introduce the competition winner to take the majority of the time. So I just wanted to acknowledge that many people have contributed to the data sets that made this prediction competition possible, over 10 years of work from many in this community. So it's pretty incredible. Essentially, our competition was giving the competitors all the data we had so far in the Genomes-To-Fields project and asking them to train a model with it and then predict what would happen in 2022 without having that knowledge. It's quite a difficult problem because it was a new year, so some component of environment, but also almost entirely new genetics. So it was actually a very difficult problem. I just wanted to say we had really incredible, enthusiastic participation from all over the world. It was really incredible to see the interest that people had. And I also wanted to just briefly mention, particularly at the top, the top 10 was quite competitive, really quite close, and people used all sorts of different modeling strategies, and many were able to do very well. So we're working on writing up a publication about all of this. So look for that to come. But now I want to just introduce Alencar Xavier to come up and present about his winning model. So let's congratulate him on his win.
All right, thank you, Jacob. We'll jump right to it. So here's a brief outline of my presentation. So I'm just gonna talk a little bit about our thought process and how we perceive the data and how we went about to do our modeling. All right, so a little bit about our team. So the name of the team is called CLAC because we are a team of Latin America corn people from Corteva. To be fair, I am in Johnston. The other people, each of them are from a different location. And then you may wonder, so how come we did the prediction in North America so well? So it turns out that most of us have a degree from an American institution. All right, so the first thing that crossed our minds, and that's a slide I presented to my colleagues when we got the data first and we read the rules, was about the evaluation metric. So here I have a evaluation scenario, the criteria where I was trying to illustrate to my team how the RMSE works. So I have two scenarios here, and you may wonder, you may look at them and see right away which one is better, which obviously is scenario 2, right? So the funny thing about RMSE is that it doesn't care about ranking. And that's particularly hard for us that work with breeding because we care about ranking lines within environment. But here, RMSE, if we get the mean of the environments correctly, we are better off than get the ranking correctly. So if you look at the trend in the graphics, you don't get why scenario 2 is better, but if you look at the scale, you see that the average prediction in scenario 2 is much closer to the average, to the scale in scenario 1. So really we are, because the name of the project is Genomes-To-Fields, we really are trying to predict phenotypes in a scale that is as close as possible to the scale of the genotypes to be predicted. So some considerations that the ranking here is, it means far less than getting the environmental means correctly. Another thing is that shrinkage is our enemy. We want to get things in the scale of the phenotype. So we know when we do the GBLUP and all those regularized machine learning, we are going to get some shrinkage, and that's not what we are looking for. So in that idea of precision and bias or unbiased, we are really looking for getting results that are unbiased. Of course, if they are precise, that's good, but they can be not precise and still give very good loss function. Okay, now I'm going to describe a little bit of the data we got and as we perceived this data set. So the genomic information came from all the 5,000 individuals. There were 400,000 markers. And because there are so many markers, we tried to squeeze as much QC to drop for any possible reason we could have to drop a marker we would. All those computations were done in my personal computer. We didn't really use any cluster or anything. We were provided with environmental variables, presumably from source, possibly from EnviroType, which is the weather from the NASA Power, and some soil data. And we also got some metadata that informed about treatments, irrigation, or dry trials, as I illustrated in the bottom right scenario here, that we ended up having to pull the levels. All right, so as for the TPG, target population of genetics. In this graphic, it's just a principal component analysis where I'm trying to show where are our genotypes from the estimation set and where are the genotypes from the prediction set. We know that the more closely related the prediction set is to the estimation set, the better our predictions will be. And fortunately, I suppose, we see that our prediction set is somewhat within the scope of the prediction set. But there's no clear overlap that would say, wow, that's extremely related, right? So okay, as for the TPE, the target population of environments, one nice thing is that we have data from several years and is reasonably balanced across years. Another thing that's very nice and it makes the whole difference in this type of prediction competition is to know that every environment we are trying to predict in the 2022 data was previously observed in the past. Meaning that we are not trying to predict an environment that has never been seen, at least in terms of location. Of course, in terms of year location, it's fairly new. Some locations in the estimation set were not necessarily relevant. We had one in Europe, in a couple locations where they are not necessarily overlapping with any of the prediction set. So we have some in Colorado here, some in Tennessee. So those are the good candidates to drop, and some in Ontario as well. All right, now to the modeling. So what exactly we're trying to model? Here, the way how we were thinking about G by E was more in G given E as, phenotype given environment. So we are trying to predict the location mean, particularly the location mean, because based on on the evaluation criteria, that's the most important thing, and the genetic effect inside that location. So we are trying to do this prediction in 1,100 observations. We're trying to predict hybrids in 26 locations, and there were 548 genotypes, from which only 43 were also observed in the estimation set. And the number of genotypes per area of interest ranged from 300 to 500. So the genomic information, as I alluded to earlier, there were 5,000 hybrids. The data was provided not on the parental level, but on the hybrid. So even if we wanted to go to the GCA level, we wouldn't be able to. So the data would have to be modeled at the hybrid level. And as for the QC, one thing that I thought that was important is when I was QCing the markers, I wanted the MAF to be at least 0.05 in the estimation set and in the prediction set. So the threshold had to be higher than 0.05 in both, because I want those alleles to be segregating in both estimation and prediction set. You know, and again, after some serious QC, dropping the SNPs for any reason we could find, we got to 150K, but it's still too many. It doesn't make sense to us to run the computation in a regression type of approach. So I thought that we would benefit from reparameterizing the model. So we need some reparameterization to really reduce the dimensionality. So how do we go about that? There's this thing called the kernel trick, which entails in creating a relationship matrix. You know, if I didn't say before, I would say now. Our model was basically a gblup. So I used the arccosine function to create a relationship matrix. I took this relationship matrix and ran an eigendecomposition just to recover the principal components matrix, which is this matrix M. So why would I do that? Because then with the M matrix, I can run a regression type of model, no problem. And that would be equivalent to have run the relationship version of the same model, which is the gblup, right? So it's just a minor reparameterization. And again, instead of modeling now the 150,000 markers, instead I'm just modeling 5,000, so that the data become much smaller, so I can very easily do that on the computer. Now a little bit about the formatting of the data. We were able to extract the location and the year from the name of the name of the environments. For previous crop, we had to do some pooling. There was too many levels, so we had to take, say, peanut and soy and call it legume. The treatments, everything was called, you know, we pulled some levels, irrigation early, standard, we called everything standard. Then everything that had irrigation as metadata or had irrigation in the treatment was called irrigation as a single dummy variable. And there were 3 locations that there were, the levels were pulled when there were too few levels. That's the whole idea of saving degrees of freedom. And just to let you know, some of the locations did not have metadata. 3 of them did not have environmental information. As for irrigation, I thought it was very interesting that in the estimation set, there were 3 out of 217 locations that were irrigated, but on the prediction set, it was 9 out of 26. And there's many more on the prediction set than on the estimation set. And for the yield, the very rough QC would be just drop everything that's outside of 3 standard deviations from the location mean. So our winning model was an average of 2 gblups. Model A was a very simple, single univariate gblup with no spatial adjustment, nothing. Just, you know, means of the environments as fixed effect, genetics as random. And model B is a little bit of highly processed data, but still does not departure from a gblup. It's funny that one may expect that it will do something very sexy, but the winning model ended up being a very simple gblup. So now I'll describe those 2 models. So as for the first model, as I said, very simple gblup, station, treatment, irrigation, and random effect was hybrid. We just check which things we'd consider as fixed effect. So we just did a very simple likelihood ratio, just include previous crop, irrigation, and treatment. And the line of code that solved model A was just the single R statement. So to be fair, my line of research is algorithms and solvers. So that's my time to shine. I use my own package to solve the model A and model B. And here I'm just providing the publications of the package and of the method. As for model B, which was a little more complicated, we decided to do as follows. Location mean and location variance will be modeled separate from genetics. So it's highly engineered because we're gonna use only environmental data to get the mean and the variance, and we're gonna standardize the genetics and get a standardized genomic prediction so that we decoupled the scale and the mean of the environments. And that was our pipeline to predict mean and standard deviation. We first just pull the data to mean and standard deviation of every location. That's going to be our response variable. We model using an average of 3 models. So there was a little bit of an ensemble here. A random forest, a penalized regression, and a ridge regression. Some using environmental covariates, and the ridge regression, just the same X that I use in the model A. And the funny thing is, without the environmental covariates, if I was to run a quick cross-validation, I would get a much higher correlation. And that's tipping something off that I'll touch on later on, that most of the information came from this very simple term as opposed to the environmental covariates. We averaged the 3 and then fit a linear regression to get rid of the bias. Okay, so that was the mean and standard deviation. Now, how did I get the genetic ranking of the lines? I ran a spatial adjustment within each location. I fit a multivariate model treating all 217 locations as different traits. And then I just created like a selection index because, I got this 317 predictions for all the environments, so I just had to create a way to summarize those. So that's the multivariate model I use, which allows each environment to have its own heritability, and it measures the correlation between all the environments. So all the G/E correlation that we captured really came from this model here, where we are checking how similar environments were. As for how we combine the data, we use the selection index, and that selection index was based on the deterministic accuracy, which can be calculated based on the covariance between our prediction set and estimation set, and as a function of the heritability. So that's basically our index, is how and where we are inputting the G/E into the model. And then the index basically was a function of a little bit for all the environments, a higher weight if you are in the same state, in the same station. And why multivariate would be any better? Basically, every time that you do a multivariate, there's a little bit of information gain, because if 2 environments are correlated, you get to capture that correlation. And if you don't believe me, I just explicitly made the derivation to show that any breeding value coming from an univariate will have this formula here, and if it's from a bivariate, we would have all these extra Greek letters here, a little extended. All right, so that was the idea of Model 1 and Model 2. Oh, sorry, Model A, Model B. And I'll tell you how did you get to average those and be our final submission. So the prediction competition allows us to submit up to 5 models. First, we submitted Model B, the very complex one, because we thought that complex was good. And our MSE was not great. We did some QC. Instead of getting better, we got worse. So we learned that QC in the data it can be detrimental to that prediction. The third model was an average of the first and the fourth submission. Basically, I thought, well, if you're not doing too well on just a single model, let's average them. And because the third was the average of the first model and some new proposed model, I thought that if I just went for the new proposed model, it would be even better. So that's why I resubmitted as Model 4, where I did the QC GBVs, but no environmental covariates. And finally, we just decided to average with a uncooked GBLUP. And that's when the whole magic happened. So on the right here is the within environment correlation. And we noticed that once we average with the GBLUP, we had a big bump into predictive ability within environment. Here I'm just sharing some what ifs. What would have happened if the competition had a different evaluation metric? And it's interesting that, for different evaluation metrics, our team will not be the one winning. But I was very glad to know that if the metric was the correlation within environment, we would still have gotten the first place. Here's just to show how our MSE would correlate with the within location correlation. And that's by no means a very high correlation. And one thing that you may notice is that the person who got second place doesn't have within location correlation. And that's because the guy modeled just environment. He didn't model genetics. And still was really hard to beat him. Meaning that our MSE really was a function of the environmental means, because the guy didn't even have G or G/E in his model. That was amazing. All right. So just a final remark, because I already ran out of time. It's the evaluation metric really valued the location means. We did have some environments that were observed both in the prediction and estimation sets. And our best model was just an average of 2 GBLUPs. And thank you, and I think I'm open for any questions if I might.